Hello, thank you very much for watching my presentation. In what follows, I'm going to describe work done in collaboration with Patrice Godefroy and Marina Polisuk from Microsoft Research on testing cloud services through the REST APIs. In the context of this work, we specifically test cloud services with an eye on desirable security properties. Cloud services, like those running in Azure and AWS, form a rapidly evolving ecosystem as reflected by the growth in terms of market revenue. This growth will likely increase further since due to the outburst of the COVID-19 pandemic, more and more educational institutions and companies are adopting a remote working environment, which is pushing further the need for cloud services. As shown by measurement studies, REST APIs is one of the most prominent ways developers use to access cloud services, and usually these REST APIs are documented with interface specification languages such as Swagger and Swagger OpenAPI specifications. Given the ubiquity of cloud services, testing is clearly of paramount importance in a multi-billion-dollar market. Next, I'm going to describe approaches that have been used to test cloud service REST APIs. First, one way to test REST APIs is by using grammar-based fuzzers. In grammar-based fuzzing, the tester has to manually specify a grammar of rules describing how to fuzz each API endpoint. The main challenge is the manual effort required, along with the fact that a new grammar is required for every new service. Furthermore, there is no coverage information obtained by the service under test, which is being treated as a black box, and therefore there is no way to know how much fuzzing is enough, which fuzzing rules or fuzzing values works best. Second, since RESTful cloud services run on top of the HTTP protocol, another approach to test REST APIs is by using HTTP-layered network fuzzers. The main challenge of these approaches is that they require live traffic, which they then fuzz and replay with the hope of finding bugs. Another challenge here is the fact that these approaches are not stateful, meaning that it's unlikely to explore new service states that require sequences of multiple dependent requests. Third, there have been solutions based on custom tools for testing specific APIs, which are labor-intensive to build and have a high maintenance cost because APIs tend to evolve over time. Most recently, grammar-based fuzzing has been automated in the domain of REST APIs by Wrestler. Since most production cloud services are programmatically accessed through well-documented REST APIs, as shown before, Wrestler performs a lightweight static analysis on the API specification of a target cloud service and infers dependencies among request types. Then, Wrestler automatically generates a fuzzing grammar that encodes sequences of requests instead of single requests in order to test the target service more deeply in a stateful manner and uncover unhandled exceptions, commonly known as 500 internal server errors. Although stateful REST API fuzzing has been successful in reporting multiple bugs in production cloud services, unfortunately, these bugs were exclusively unhandled exceptions, which are visible through the 500 HTTP status code. The challenge of this work will be addressing how to uncover errors that do not cause visible 500s. To this end, first, we will introduce rules that capture desirable security properties of cloud service REST APIs, and we will show how to augment stateful REST API fuzzing with checkers that actively suggest new appropriate tests and seek for violations of these rules. Obviously, violations of these rules will be the target errors of this work. Excuse me. In the remainder of this presentation, I'm going to describe 3 selected security rules that capture desirable properties of cloud service REST APIs. Then, I will describe how stateful REST API fuzzing can be augmented in a modular way with active checkers that test violations of these rules. And finally, I will discuss selected errors found with our checkers in Azure and Office 365 cloud services. First, we start with the description of the use after free rule. At a high level, the desirable property captured by this rule is to ensure that resources which have been deleted are indeed no longer available, no longer accessible. For example, deleting a message stream with a unique ID 1 and then trying to access it must always fail. Otherwise, we have a violation of the use after free rule, since an allegedly successfully deleted resource remains usable, which is dangerous and clearly not desirable. Next, we continue with the description of the resource hierarchy rule. At a high level, the desirable property captured by this rule is to ensure that the child resource, which have been created under a specific parent-child hierarchy, is only accessible under its originally assigned parent resource and not accessible from other parent resources. For example, if we create 2 posts with unique post IDs 1 and 2, and then only create a reply to the post with unique post ID 1, trying to access the reply through the post with ID 2, which is not its parent, must fail. Otherwise, we have a violation of the resource hierarchy rule, since a child is accessible from another not originally assigned parent resource. Finally, we describe the resource leakage rule. The desirable property captured by the resource leakage rule is to ensure that the resource which was not created successfully is not accessible and does not leak any side effect to the backend service state. For example, failing to create a post, say with unique ID 1 that is receiving a 404 or a 500 HTTP status code, and then trying to access such a post using the unique ID 1 must fail. Otherwise, we have a violation of the resource leakage rule, since a failed resource creation caused some side effect on the backend state instead of failing cleanly. Having finished the security rules description, I will now go on into describing how stateful REST API fuzzing can be augmented in a modular way with active checkers that test for rule violations. As mentioned earlier, stateful REST API fuzzing is implemented by Wrestler, which I'm going to briefly describe in order to give some background. On the left-hand side, we see Wrestler, and on the right-hand side, we see the sketch of a target cloud service with a REST API. Wrestler uses an automatically generated fuzzing grammar and its testing driver to produce generic tests, which are stateful sequences of API requests, and execute such tests on the target cloud service, hoping to trigger 500 internal server errors. While Wrestler executes generic tests, a set of checker hooks monitors the latest generic tests and each time invokes the checkers that are applicable. And I will explain this next with a few concrete examples. Okay, here for instance, if a generic Wrestler test deletes a resource, the checker for use after free violations kicks in and checks if a use after free violation occurred. If so, the specific use after free violation is treated as a bug and the respective test case will be saved for further manual inspection. Similarly, if a generic Wrestler test case creates a resource, the checker for resource hierarchy violations kicks in and checks if a resource hierarchy violation occurred. If so, the specific violation is treated as a bug and the respective test case will be saved for further manual inspection. Finally, if a generic REST test causes an error, for example, a 500 HTTP status code is received, then the checker for resource leakage violations kicks in and checks if a resource leakage violation occurred. If so, similarly, the specific violation is treated as a bug and the respective test case will be saved for further manual inspection. Okay, at this point, we are done covering the security rules introduced in this work, selected security rules. For more details, you can look up into our paper, as well as the implementation of the active checkers to capture the respective violations. Next, in what follows, I will discuss selected errors that were found by our checkers in Azure and Office 365 production cloud services. The targets of our evaluation were 3 cloud services from Azure and Office 365. We omit explicitly naming those services to avoid targeting them. However, we note that all 3 services were production scale services with publicly available API specifications, complex API request formats, and approximately an average of 16 API requests each. I'm going to describe 3 selected errors found with the aforementioned checkers. First, we found a use after free violation in an Azure service. The specific test case that uncovered the error at point consists of 3 requests. One, first request that creates a new resource called R. Another request that deletes the resource R, seemingly successfully. And the last request that attempts to create a new child resource with R as its parent and receives a 500 internal server error. Okay, so let's think about this. This is a use after free rule violation because instead of a 500 internal server errors, the desirable behavior would be a 404 resource not found HTTP status code, since the resource R was seemingly successfully deleted. Second, we found a resource hierarchy violation in an Office 365 service. The specific test case which uncovered the error at point consists of 4 requests. 2 requests that create 2 distinct blog posts with unique post IDs. Another request that creates a post reply, which is a child resource, to only one of the 2 posts. And the last request, which edits the post reply through a parent, which is not the originally assigned parent of the child resource, and receives no error. This is a resource hierarchy rule violation regarding the original child-parent relationship between the resources. Third, we found a resource leakage violation in an Azure service for network resource management. The specific test case that uncovered the error at point consists of 3 requests. One that creates a resource of type T with name X, but using a malformed request body. This results in a 500 internal server error. Another request that queries the list of all available resources of type T, and this results in an empty list, which implies that no resource of type T and name X exists. Finally, a last request attempts again to create the resource with name X and type T and receives a 409 HTTP status code, implying that the initial failed creation of resource X led to an inconsistent backend service state instead of failing cleanly. This is a resource leakage violation. Okay, in conclusion, in the context of this work, first, we introduce rules that capture desirable security properties of cloud service REST APIs. Then, we extended stateful REST API fuzzing with active checkers that capture violations of such rules. And ultimately, we use these active checkers in order to test production Azure and Office 365 services. Notably, All bugs found in the context of this work were reported to the respective service owners and have all been fixed. Thank you very much for your attention. In this slide, you can find a link to our paper with many more details on our work, and don't hesitate to contact me or my co-authors with any further questions.